What is the significance of measuring impedance under open circuit conditions, and how does this compare to measuring impedance under discharge or charging conditions? What happens to the impedance when the system is in a discharge condition, and how is this different from the impedance measured during charging? What role does the high frequency play in experimental measurements, and how does it relate to the highest frequency given to the AC disturbance applied to the system? Why is it important to understand the concept of high frequency in the context of electrochemical impedance measurements? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What is the purpose of applying a low frequency to the system, and how does this lowest frequency impact the measurement process? How do high and low frequencies work together to provide a comprehensive analysis of the electrochemical system, and why is it important to control both frequencies precisely? How does the amplitude of the AC disturbance affect the measurement process, and why is it crucial to set the amplitude to an appropriate value? Why is it important to have smaller amplitudes for more accurate results, and what potential drawbacks can arise if the amplitude is too large, such as increased noise signals? What is the role of noise signals in electrochemical measurements, and how can they interfere with the accuracy of the data? What is the concept of resting time in experimental measurements, and why is it necessary to allow the system to rest before taking measurements? How does the resting time ensure that the electrode material is in full contact with the electrolyte, and why is this full contact essential for accurate impedance measurements? What impact does insufficient resting time have on the accuracy of the measurement, and how can it affect the overall results? How does the resting time help to stabilize the system, and why is this crucial for obtaining reliable data from the experimental setup? What does it mean when AC impedance is controlled by a mixture of charge transfer and diffusion processes, and how does this affect the shape of the Nyquist curve? How does the Nyquist curve typically appear when the electrode process is controlled by both charge transfer and diffusion, and what are the key features of the curve in both the high frequency and low frequency regions? Why does the Nyquist curve consist of a semicircle in the high frequency region, and what does this shape represent in terms of electrochemical behavior? How does the semicircle relate to the charge transfer process, and why is this process dominant at high frequencies? In the low-frequency region, why does the Nyquist curve transition into a slope line, and what does this line represent in terms of the diffusion process? How is the low-frequency region controlled by the diffusion of reactants or products?